Welcome, everybody. We'll let everybody log on. And sometimes it takes a few minutes for everybody to get out of the waiting room into the hall, I guess you could say. And then we'll start in just a couple minutes. While we're waiting, I'd encourage everybody who's already logged on to change your name on your Zoom name so that we can see who's in attendance. That really helps us for you getting any certificates of attendance from either the county or from, if you're a code official, from the Department of State. To do that, what you'll need to do is you hover your mouse over your own picture or your name, if your camera's not on, and you'll see 3 dots in the upper right-hand corner. And if you click those 3 dots and scroll down to the bottom of the list, it says rename. And click on rename, and then you can write in your new name. Your full name would be helpful. It really does help with attendance. The other thing that we'd like you to do while we're waiting for everybody to log on is to write your name in the chat. And if you could say what community that you work with, which town or village, county that you work with, that'll help everybody to know who's with us and where you're from and so forth. And if you're now, some of you might be logging on from your phone. It's a little bit different, but on your computer, if you down near the bottom of the screen, there's a bunch of small icons, and the word chat should be there. And if you click on it, then you can type your message there, your name and your community. That'd be super. We can see that we got already have a few communities represented: the Village of Constableville, Town of Ellisburg, Village of Messina. Thank you for attending. And thank you for changing your names. A couple people only have first names. If you wouldn't mind putting your last name, that would be helpful so we can, figure out who you are for attendance. But I think we can go ahead and maybe get started. My name is Nancy Bernstein. I am the Clean Energy Communities Coordinator for the North Country region. I work with the Adirondack North Country Association. My official title is an Energy Circuit Rider, but I work with communities, municipalities in particular, to help implement energy efficiency and renewable energy projects in their community. And we welcome you to this series. This is a 5 workshop series that is being presented through the Clean Energy Communities program. That's a NYSERDA program specifically geared towards, getting or encouraging municipalities to take clean energy actions for their community. This workshop, Understanding Solar PV Permitting and Inspecting, is being presented by Chris Doty from Frontier Energy. But before we get on to the presentation, I again want to ask you to change your Zoom name so it reflects your full name. And if you haven't done so, to put your name and your community in the chat. And mostly, I just wanted to thank everybody for your service to your community. I know it's a big ask, and we really appreciate everything you do, where you live. Let's see. Lauren Tabalt is here from Lewis County. She's a community development specialist. And I believe Lauren has a few things that she was going to say from the county perspective.
Yep. Thank you, Nancy. Hi, everyone. For those of you I haven't met, I'm Lauren Tabalt. As Nancy said, I'm a community development specialist in the Lewis County Planning Department. And we're looking forward to this evening's session on solar PV permitting and inspecting, because as solar developments continue to be sited in and around Lewis County in our case, it's become more important for us to have a better understanding of these processes that take place so that we can help to ensure safe and efficient developments right from the get-go. So with that being said, we're looking forward to learning more about this topic from NYSERDA, and want to say thank you to INCA for setting up these opportunities for us to learn more.
Well, thank you, Lauren. Just for another housekeeping piece of information, we will be providing the slide deck, Chris's slide deck, and a recording of the webinar after the session. Give me a couple days and I should get that out to you. If you provide your name, and for those code enforcement officers, also please provide your New York State training ID number. Then we will be able to get your certificates to you. Each individual county is responsible for sending certificates of attendance to any planning or zoning board members. And they've been doing that for the other sessions that we've had. But the Department of State attendance will need your training ID number. If you didn't put that in your registration, I have that for several people, then you can either email it to me, or if you want to put it in the chat, we'll have all that information afterwards. Otherwise, I think that's about it for getting ready. I'd like to introduce Chris Doty from Frontier Energy. Thank you very much, Chris, for providing some information tonight.
Thank you for having me. So let me share my screen. I'm assuming everyone can see that.
Yes.
All right, great. All right, so welcome to the Solar PV Permitting and Inspecting in New York State course prepared by NYSERDA. I'm an engineer. I work at Frontier Energy. I've been an engineer for about 11 years, and I'll be presenting this to you today. We have a lot of material to cover, so we'll be moving through pretty quickly. And just kind of an overview, the purpose of this presentation is sort of to give you kind of a 10,000-foot view of the Unified Solar Permit, or USP, and the inspection process. And it's not really to give you specific answers to specific situations, because that would take many hours to do. But if you do have specific situations you come across that require additional information, or you need a second opinion, NYSERDA is always happy to help with those, and you can email me at this email address right here if something like that comes up. Like I said, we have a lot to go through, so we'll go over questions at the end of the session, so we can get through all the material. Just put your questions in the chat when you have them. And if you can reference the slide number, that would be helpful, to just kind of reference where we were in the presentation. And if we go until the very end and we don't get to your question, just feel free to email me again at this email, and I'll be happy to get you an answer. So let's jump into it. All right, so this course is registered for 2 hours of Department of State in-service training credit. First one is for enforcement and administration. The second is for uniform code. This is the course number right here. And just to go over kind of attendance requirements, you have to be logged in within 15 minutes of the scheduled start time of the session, which all of you are, because it's within 15 minutes of the scheduled start time. And to get credit, you also have to, you can't log out until the scheduled end time, or until we're done, to 30 minutes after that. And then there are pretty strict requirements on that, so make sure you don't log out early, or if you know someone that's supposed to be on the training and isn't yet, tell them to get on quickly. All right. So the Division of Building Standards and Codes won't give credit for attendees that aren't, I guess, paying attention to the screen, since this is a virtual training. So you have to keep this Zoom window as your main screen. Otherwise, that will reduce your attention to duration ratio, and then you won't get credit for attending the course. All right. So that's about all for kind of announcements. What we're going to go through today, we're going to go into the solar permitting, which is the New York State Solar Unified Solar Permit, which is kind of a general purpose permit that I sort of put together to help help communities kind of expedite the solar permitting process. Then we'll go into some field inspection overview, and then labeling requirements, and then common errors found at site inspections. And then if we have time, we'll jump into some Q&A. All right, so the New York State Unified Solar Permit. At the time that slides were made, which was a couple of years ago, over 300 communities in New York State had adopted the USP. It's an easy process. It can be done by local law or by adoption by the local government. The USP is kind of a best practice. It includes requirements that can be applied to all solar PV systems of any size. It was originally made for residential systems, but it can be applied to systems of any size. So why is the USP such a powerful tool? It streamlines the process, and it kind of standardizes everything so that it's consistent, predictable, and repeatable, and it can be duplicated across multiple authorities. And that means everyone's looking at the same things, and they can move permits through more quickly while still maintaining quality. And it can be used by permitting authorities, by contractors, by the community, so everyone knows the documentation needed to be submitted to successfully get your permit. And obviously, the whole point of the permitting process is to make sure the installations are safe and code compliant. All right, so this is the first 2 pages of the application, of the permit, the Unified Solar Permit. It's basically the application section. It's sort of a cover sheet for the application. It doesn't have a lot of technical information, but it's kind of more of a who, what, when, where, and why for the permit. So the first thing on the first page is to determine if you're eligible. If you can check yes to all these 6 items, then you are eligible to use the USP. It's just mainly simple things like verifying the size of the system, to determine if you need like a historical review, or if that review is already complete, or if you need a special electrical permit or things like that. And if you can check yes to all of these, then you do qualify. And then the permit also has dozens of customizable fields so that you can adjust the template to work for the needs of your community. So you can add in permitting fees or schedules or things like that to allow contractors to have all this information in one spot. So this next section, this describes the submittal requirements of the applications, and here's where you can, customize the specific fields. Like I said, you could adjust the fee schedule, the permit, or the payment methods, and you can put in your website and email, just so contractors have it all in one spot, so it's easy for them to find. And then the next section down is in the application, it spells out approximate timelines contractors can expect for review and response or review and denial of an application. They may be 2 different timelines. If you get an application and something is very obviously wrong, you can deny it very quickly. To go through the whole proper application and permit and make sure everything is in line, then it may take more time. So maybe 2 different timelines for that. And it'll give solar contractors a clear expectation of when they'll hear back from the permitting authority. The next section is the first section on page 2. It includes standard, owner and dwelling information that's seen on all types of permit applications. It does include the same information contained on the local tax maps, such as section, block, and lot number. That would be contained in the tax records, and that's to make it easier for the AHJ to reference and to know the exact plot of land that the work will be done on. All right, so the next section is kind of a very concise and clear snapshot of the system, including the basic size in kilowatts DC, the type of inverter, and the location of the interconnection. With respect to the service disconnect, we'll go through these things a little bit later in the presentation. There's 2 types of connections to the utility: a supply side, which is ahead of the main disconnect, and load side, which is typically a backfeed breaker or a sub panel. With the inverter, you can have a microinverter, a string inverter, or a DC optimizer, basically. And if you know those characteristics of the system, you can have a pretty good idea of what equipment will be in the system without even looking at any of the other documents. So you have a good kind of snapshot of what's going to be there. So the next section is detailed contact information for the contractor and the electrician. It includes the contractor and electrical licensing numbers where applicable. And then one of the important things to notice for this section is the property owner's signature and the solar, the contractor in doing the installation have to sign and date the bottom of the application to make it valid. All right, so now the application portion is filled out. What documents are required to accompany the application? There's 3 pages here you can see of extensive information that's required to be submitted with to be compliant with New York State laws, construction documents, and other information that's critical to evaluate the system. And these requirements are basically the same for like a 25 kilowatt system up to a megawatt system. It's like I said, this USP is built so that it can be applied to any size system. And some of the things in here may not necessarily be applicable to each system, but you just mark those as not applicable and then move on. All right. So, like I said, in the USP, there's a lot of customizable fields, and that is a place where you can add specific local requirements when there are some. For instance, like if you require a separate electrical permit or a separate building permit or fire department approval, you can add that all into this section. And this is kind of your opportunity to customize the standardized process for your area requirements. And it allows the permitting authorities the necessary bandwidth to ensure they request the information that works best for their departments. And it also makes it easy to review and helps contractors not miss anything that's necessary in a given jurisdiction. All right, so the construction documents that are required to come in with this. We'll go through these in a bit greater detail as we move on, but the most important thing to remember is they have to be stamped and signed by either a New York State registered architect or a New York State licensed professional engineer. And this is that professional taking responsibility for the quality and the accuracy of the design, along with specifying the information or the equipment and the materials that are going to be used. As the code official, it's your job to determine code compliance and make sure that the installation is code compliant. But you shouldn't be taking the design responsibility also on your shoulders, because it's not, that's not the requirement of the code official. It's the engineer or the architect's job to put together the design and take responsibility for that. All right, so now we'll go through some of the documents and kind of what we'll be looking for. Different documents have different things that we need to check. So firstly, we'll go through kind of the electrical details, which has an electrical diagram, and it has all the components of the system, so it allows the contractor to carefully consider each in the design and detail the specifics, so the local code official has them kind of easily laid out for their review. And this includes all of the components from the modules, the array, to the utility interconnection. And each item has to be accounted for. Next is the roof plan or the site plan. This is a detailed site plan that's required. It indicates the specific location of all the major components, including rooftop access and setback requirements and a few other things we'll go through in a couple minutes. And then there's a structural review, basically, that has to be submitted. And this is every every structural review is site specific. It has site specific information because every solar installation is different, right? And every roof is different. Most of these likely will be for systems installed on roofs. So this basically goes through and makes sure that the roof structure can hold the solar panels, and it has the quantity and the locations and the loading calculations for the framing of the roof in it. And there are checklists for each of these that we'll cover later. All right. For inspections, which inspections are required by the AHJ? So in the USP, you can clarify all the items that are required for the inspection, so there's no surprises for the contractors. The inspectors will not only be looking to see that everything's code compliant, but that the construction matches the proposed design. And this is done in a systematic way by going through the checklists that I mentioned a second ago. And it helps to reduce human error and make sure that all the components are accounted for and as designed. And so NYSERDA does require that photos be taken on all the systems that are receiving NYSERDA incentives, which should be 99% of systems. This is important because sometimes access is not easy, and sometimes things that need to be inspected are covered up during installation. So it's important for the local contractor or whoever's installing the system to take photos throughout the installation process. And provide those to you, the local inspectors, so that you can kind of see a story of how the installation went. All right, and so there's a few questions throughout the presentation. So here's the first one: which item is not a requirement of the solar PV permit application? If you want to just put the answer to that in in the chat, then I'll give you 30 seconds and then we'll go over it. And, hopefully everyone got that in. You won't be graded on it or anything, but just to make sure you're paying attention, I guess. So the answer is you do not have to require or submit proof of payment of property taxes. The site drawing, the wiring diagram, and the contractor's telephone number are all part of the application and the required documents, but the proof of payment of property taxes is not. All right, so now you've received the permit package. It could be the standard package your department receives or the USP. The tools in this next section will help you kind of review the permit package. All right, so NYSERDA has developed a bunch of tools to assist in the permitting authorities in their work. The design review checklist, which is mentioned here, and a field inspection checklist, in addition to the quality assurance checklist, which all are available through the NYSERDA website. They're comprehensive tools designed by professionals with experience performing thousands of inspections. So NYSERDA has done over 4,000 inspections as of probably a year ago. So it's probably many more now. But we'll take a look through these checklists in more detail. And one thing to keep in mind is a lot of this can be found in the New York Solar Guidebook, which is available through NYSERDA at this link right here. It has it's very comprehensive. It's a detailed collection of information. It can be useful for contractors, permitting authorities, plan reviewers, inspectors, pretty much anyone wanting to install a solar system. And it's continuously updated, and new chapters are being added to reflect changes in the industry. So it's a very useful resource, and I would encourage you to use that if you find it helpful. All right, so starting with the design review checklist and its main components, the requirements for the site plan, the details of the electrical diagram, and the review of the structural analysis. We'll go through these, and all of these need to be looked at thoroughly to determine code compliance of the system. And like I said, all are available in the guidebook with code references included, which is very handy. All right, so for a site plan, it's basically like a walkthrough of the components of we'll go through a walkthrough the components of a detailed site plan, and it basically outlines the equipment information, including kind of the location of key components and any trenching. Has setback requirements included in that, so you can help avoid having to remove and replace equipment if they're too close to the property line. And you want to go through kind of each section in order to avoid mistakes. All right, so here is an example of a site plan. It's not a perfect site plan, but it's a site plan. And what you want to do is you want to take a closer look at key items. You want to make sure that there's in this one, it's on a rooftop. You want to make sure that there's rooftop access. You want to verify the location of the meter, the inverter, all of the different components in the solar design. You want to make sure it has the correct address and tax information. And you also want to make sure that it's design the professional engineer or the registered architect has stamped and signed the drawing. And I think that's about it for that one. Next, we'll go through the electrical checklist. So you want to take some time and go through every single item in the electrical checklist one at a time, and compare the checklist to the electrical diagram, make sure everything is accounted for. And you want to point out the details of each item, and make sure that, like I said, everything is accounted for. There are no missing components that should be there, and make sure that all the equipment is compatible with each other. And then this is kind of an example of what it may look like when you're done. Some things may not be applicable, but you want to make sure that everything that is accounted for is checked off, and make a note of anything that's missing. And this will allow you to, when you go on site to do the inspection, you can just verify that the things that look good in the design are there and are installed correctly, and you can have more time to spend looking into missing information or design issues. And one thing to keep in mind is there is a difference between a code review and a design review. For instance, a design issue may be if a disconnect switch is not labeled for the voltage or the DC rating, but that may not be a code violation yet. So you would verify that during the actual inspection when you see what's actually on site. And so just going through the checklist makes it easier for the reviewer to not miss details, and it can expedite the process of going through to make sure everything is done the same every time, and you can move through more quickly. And that you would do all of this prior to issuing the permit. This is more on the electrical checklist. As you can see, this allows you to go through and verify that the equipment and the calculations are done correctly, and there are no missing pieces of information that would be necessary to evaluate the system. And next, we'll go through the structural analysis. Like I said, for the previous two checklists or previous two documents, you want to go through each of the items in proper order, make sure that you hit every single piece, and make sure all the values are accounted for and that the calculations have been filled in and properly done. Like I said, this in particular is very site specific because every solar design is different and every roof is different. So you want to make sure that all of the correct values are filled in the section, and and everything is accounted for, and all the calculations make sense. All right, like I said, one size does not fit all. You want to make sure that the plans have the signature and stamp of the professional engineer or registered architect. Like I said, that's them taking responsibility for the design and, you know, taking the responsibility squarely on their shoulders. And that's their job, so they need to do that. That's not the code official's job, because you don't want to take that responsibility and be responsible if something is not designed correctly. All right, so now the design review has been completed and the permit's issued. The next step is the inspection. So what's the next step? What do we do now? And have we considered the safety of the inspector? So inspections are required to follow the NFPA 70E, which is the standard for electrical safety in the workplace. And of course, OSHA requirements. Everything needs to follow OSHA requirements, but the NFPA 70E has traditionally been for electrical workers, but now has been updated to include inspections as well. So inspectors must comply with the standard as well. To comply with this, you would do an initial risk assessment to make sure that you have you're aware of all the job site hazards that may be present. If your inspection involves removing covers to electrical equipment, the assessment will help you determine if PPE or personal protective equipment or other methods of mitigating those risks will be required. And it's important also to keep in mind that other job site hazards may be present. You may need fall protection or other PPE that isn't necessarily for electrical safety. So keep that in mind as you go through your risk assessment. So this standard outlines procedures to reduce the risk for inspectors and electrical workers. And here is kind of the way to go through. You start with the risk assessment and you make a list of the hierarchy. There is a hierarchy of risk control methods. You want to make sure you will be able to establish an electrically safe work condition. You would estimate the likelihood of an occurrence of an arc flash incident. Hopefully it's low, because that's very dangerous. And if it is not low, you would choose arc related clothing using incident energy analysis method to make sure that you're safe in the event that an arc flash does happen. You used to be able to just kind of have an electrician on site and you can sort of stand behind them to do the inspection and let them do all the dangerous parts, but those days are kind of gone, and that's probably for the best, because you're the one inspecting, and so you need to follow the procedures to be safe and make sure that you are doing everything as safely as possible. Whoop. All right, I went one too far, but so this is the hierarchy of controls. This is a method of evaluation and selecting the most appropriate method of protection. So the main thing to keep in mind is the best control is elimination of the hazard, right? Using PPE is like kind of the least effective. That means the hazard is still there and you are just kind of trying to protect yourself from it. But if you can remove the hazard in the first place, then you don't even have to protect yourself from it. So basically what that would encompass is you would shut off the power to the system and establish proper lockout tagout, and then verify that the power is off. So that way there's the equipment that you're inspecting is not energized, and that reduces potential human error and risk of electrical shock. Because of this, many municipalities have gone to visual inspections only with no opening of junction boxes or electrical panels, and this is why. It prevents people from having to be exposed to those hazards. This is another reason that photos are required during the installation, because it allows you to see inside some of these things while they're being installed and before they're energized, which reduces the risk to the inspectors, who are typically not licensed electricians, right? So that's kind of one of the main reasons for requiring that NYSERDA requires photos during these inspections. All right, so the next slide is another question. So which of these is not in the hierarchy of control for electrical safety? And you can again put your answer in the chat. All right, and we'll keep moving. So the answer is reschedule work until after normal working hours when demand for power is lower. This is not a way to mitigate the hazard. It just shifts the time period of the hazard, which is not very useful. So like I said, ideally you would remove the hazard, shut it off, and establish proper lockout tagout. Another one is engineering controls that kind of blocks people from being exposed to the hazards, even though they're still there. And like I said, the least effective way to reduce hazards is to just use PPE. All right, so now we will go through the field inspection checklist. This checklist, like I said, it's available from NYSERDA. It's an extensive guide on what to look for. It's based on the National Electrical Code requirements, and as I said earlier, over 4,000 detailed inspections done by NYSERDA, and it's printable, which means it's easy for contractors and inspectors to take into the field. You can print it right out and then go through everything while you're at the inspection. And it standardizes the inspection process. So, contractors in one jurisdiction will have a similar inspection to contractors in another jurisdiction. So everyone knows what to look for and what will be inspected. And, you can go through them sequentially and hit all the different components of the system. Like I said, this is an organized method to review the system. So you would start at one end. Typically, you would start at the array and go down to the interconnection, or you could do it backwards. Doesn't matter how you do it, as long as you do it consistently. And this will help you move through quickly each time and not make errors if you do this, if you do it the same way each time. And so we're going to go through a basic run through of the basic items covered in the checklist from the array to the interconnection. So let's take a look at some of these components a little closer. All right, so the array. This is essentially where the panels are located, right? Here you have examples of a few different types of arrays. You have ground mounted in the middle, you have pole mounted on the right, and then you have roof mounted on the left. As you can see, the modules on a rooftop may present some additional challenges to inspectors. You may have multiple arrays like there is in this picture. You may have steep roofs, which can cause access issues and would require fall protection if you have to get up there. The roof mounted solar arrays are typically, as you can see, more difficult to do the inspection. There's a lot more room around the ground mounted or pole mounted arrays, so you can have better access to the different components in the array. And so this is a great example. A rooftop installation is a great example where construction photos provided by the contractor are very valuable. So you can, you may not have to get up and see every single solar panel. You can maybe get a subset of maybe the easiest ones to get to. And if the contractor has photos of the remaining ones, then you can use those and go from there. More on the array. What you want to do is you want to do a comparison of the electrical diagram provided by the contractor and the equipment nameplate information that's found on site. So as you can see, here we have the information from the electrical diagram that was submitted with the permit. And here we have the nameplate information for the solar panels. You can see their different model numbers, and you want to make sure that they do match. This is very important because all of the other equipment in the design is based on the solar array. So if you have different wattage panels or different panels with different amperage or even different voltage, it may not be compatible with the rest of the equipment that was in the design. And that may cause problems down the line. Designs are based on precise electrical characteristics of the modules and the string configuration, as well as the inverter output characteristics. So if equipment is substituted in the field, it may become undersized for the new electrical characteristics. A good example of this is the maximum system voltage, which is basically the open circuit voltage. So they are higher for higher wattage panels and even the same wattage modules from different manufacturers. And all of your circuit sizing, overcurrent protection, etc., are designed based on the energy production from the design panels. And you don't want to just assume that the wiring and the system components are all still compatible. If, for instance, the wiring is undersized for what you need, that can cause the wires to melt and can cause a fire hazard. All right. Another thing you want to look for with the array is the grounding of the array. The grounding and the bonding of the array is not only a code issue, but a safety issue. The integrity of the grounding system is vital to any electrical installation, not just PV, and it's dependent not only on the conductors, but also on the equipment itself, which is used to carry fault current to an overcurrent protection device or a fault detection system. In the event that there's a breakdown anywhere along the ground fault path, the fault will not be detected, and this can leave parts of the system conductive and energized and presents a significant shock hazard. So if you think about a roof mount installation, imagine a mason going on top of the roof to fix the chimney, and he accidentally touches the frame of a solar PV module. He could receive a shock of up to 600 volts DC or more, likely killing him. So this is very, very important to, grounding is one of the most important things in electrical installations because it's a safety issue, and it can, if it's not done properly, it can cause serious injury or death. So that's super important. And also we have a lot of the newer installations use integrated bonding. And so this kind of this ground lug would be an example of non-integrated bonding, and this over here on the right is an example of integrated bonding. And basically what integrated bonding is it uses equipment that serves a dual function. So this mid clamp that you see in this picture is not only used to secure the modules in place, but it also is used to bond the modules to the racking. And like I said, many of the newer arrays use this type of bonding. And on the left, you can see here the screw is coming out, and in the middle, we have a ground lug with a ground wire run through, which is less common nowadays. But like I said, it's critical that the equipment that's used to bond and ground the system is suitable for the environment and the application. If the grounding method you use is not rated for the environment, it can fail, leaving the system energized and dangerous. Basically, that's a common theme throughout this whole presentation. If you are designing a system that's supposed to last 25 years plus, which these are, you need to design all of the components to last that long. You don't want to, install it and have some of the components last, 10 years, and then you have hazards in the system. All right, this is kind of more on that topic. Like I said, it's critical to use outdoor rated equipment. Most of the equipment for these things are outside, certainly for the array. And that the outside environment has harsh elements, which, the equipment has to endure 24 hours a day, 7 days a week. Wind, rain, snow, ice, and even the sun itself can degrade equipment very quickly. So, like I said, most of these are warranted for about 25 years. So you need to make sure that all the components that are used in the system have a similar, if not longer, lifespan. And this is coupled with regularly scheduled inspection and maintenance to ensure that potential problems are detected before they cause serious issues. So on the left here, you can see that the wires are fixed in place with a black zip tie. Black zip ties are typically UV rated. The white ones,
I'm not sure.
sorry about that. The white ones will degrade after not very long, actually, and they'll fail when under sunlight for long periods. So I've seen white zip ties degrade in like less than a year. So you want to make sure that you have the UV rated zip ties. On the right, you can see another use of non-weather rated equipment. It's kind of hard to see, but here you can see this screw right here that's used to hold the ground lug onto the conduit. It's rusting, which means it's not outdoor rated, and it will just eventually, probably within a couple of years, it'll just rust away, and that ground lug will probably just be hanging there, not connected to the conduit. And typically an improper lug will show early signs of corrosion, which is easy to identify during your inspection, like rust or we'll go through things a little bit later, but if you have two different kinds of metal, you can have galvanic corrosion, which is pretty easily identifiable. All right, so moving on from the array, the next thing down the line is the optimizer or the microinverters. A DC optimizer is essentially a DC to DC converter that takes whatever amperage and voltage that's produced at the solar panels and converts it to the voltage and amperage required by the string inverter. Microinverters are essentially an inverter on each solar panel, so all the wire runs coming out of them contain AC electricity as opposed to DC. Then bringing all that together is easy in one AC combiner panel. Here we have a quick look at the checklist for the optimizers and inverters. Both microinverters and optimizers, they give module level control. So they have similar requirements in the code. It's easy to go through and make sure that everything is accounted for in the checklist. And the checklist looks for not only equipment verification, but also other details such as conductor type, proper grounding, etc. The notes at the bottom describe important details such as the labeling requirements for rapid shutdown, and microinverters and DC optimizers they're typically built with rapid shutdown requirements in their design. But one thing to keep in mind is they do require proper labeling, which we'll go over a little bit later. One thing to keep in mind for this section is what you want to do is you want to make sure that everything is installed in a code compliant way and correctly according to the installation manual. You may have to go through some of the installation guides to make sure that everything is installed correctly. But you know, that's all part of making sure everything is installed safely and correctly. So one way the DC optimizers and microinverters are similar, like I said, is the rapid shutdown feature. This is a method in the code where DC conductors are shut down on the level close to the array. If power is interrupted, the system shuts down to prevent the DC conductors in the system or building to be energized. This takes a lot of risk out for, you know, if there is a power outage or something, the solar panels won't be, the conductors won't have DC electricity running through them, going essentially back to the grid, right? So to shock the people working on the power lines. And so here's kind of a snapshot right here of the proper labeling required to meet the rapid shutdown requirements for you know, a microinverter or a DC optimizer. All right, so one more question here. True or false, using microinverters or string inverters with DC power optimizers is one way to meet the requirement for rapid shutdown. And like before, you can put your answer in the chat. Just about on time, so that's good. So we'll keep moving through so we don't get behind. The answer to that is true. Microinverters and string inverters with DC power optimizers, they do include rapid shutdown features, so that is one way of meeting the requirement for rapid shutdown, and it has to be properly labeled. That's important. All right, so next we'll go through some rooftop considerations. The guidebook has a section for rooftop PV attachments and penetrations. In addition to verifying that they're present, you have to verify that they're installed properly, and the guidebook gives us examples of the proper installation. You may see flashing that's not installed according to the manufacturer's instructions. And it's important for contractors to follow these guidelines for inspectors to know what to look for. On the left over here, you can see the flashing was installed correctly. It's kind of an odd picture orientation, but the roof is slanting down to the right. So it's hard to it looks like it's slanting up, but it's not. But you can see that the flashing was installed correctly. It's tucked up underneath the shingle. And so the water will flow down over it and it won't, you know, go back up underneath the shingle. And on the right here, you can see this flashing is done correctly, but the rubber boot would fail. And that's because the center is pushed down and water will collect there. And this can cause ice issues, and eventually the seal will fail, causing potentially problems underneath the roof and you know, inside the building. And so to fix this, you would want this rubber boot to be up more so that the water will shed right off of it. All right. Question number 4, properly installing roof flashings and sealing roof penetrations is a critical part of installing rooftop PV systems. True or false, obviously. I think this one is hopefully very easy since we just went through it. So we'll jump right in. True. Obviously, improper roof penetrations can cause leaks over the life of the system, which can cause damage to the building, or mold, which can result in costly repairs. All right, so moving on, junction boxes. There's plenty of requirements for junction boxes. That's basically an enclosure that's mounted on the roof deck. It has to be properly flashed. You can see here, this one is properly flashed. It's tucked up under the shingles, and it has to be sealed, which you can see on over here. And so one thing to keep in mind is a conductive enclosure. This is a metal enclosure. It is considered likely to become energized, because it's a metal enclosure, it's a conductive enclosure. So this would actually fail the inspection because it's a metal enclosure and it should be properly bonded to the grounding system, which it's not. The ground wire, the green wire here, just runs right through and is not connected into this, or attached to the junction box. So the junction box is not grounded. And that can cause a shock hazard. On the right here, we see this box is non-metallic, so it doesn't need to be grounded. And in both of these, the enclosures have to be rated for the environment they're installed in, like with everything else in solar installations. All right, so next we'll go through some string inverters. This section of the checklist asks for equipment verification. It's vital to ensure that the actual installation matches the design submitted in the permit package construction documents. Conductor sizing is based on the information provided by the manufacturer. And if a conductor or contractor rather substitutes the inverter model, it can be oversized for the conductors carrying the output current. Like I said earlier, if the current is too much for the wire, it can cause the wire to melt and it can cause fire hazards. So it's very important to make sure that the conductors used are rated for the amperage that they have. In this case right here, the DC conductors are coming down from this junction box up here, which comes from the roof. And you have to verify that they're in metal conduit, because all DC conductors are supposed to be in metal conduit. And they have to be labeled every 10 feet, showing that DC conductors are inside that conduit. The metal conduit provides an additional barrier in case of an emergency, so that anyone in the vicinity will not have contact with the DC wiring. And all the conduit has to be properly bonded to the grounding system. And I think that's about it for that one. In the string inverters, so going along with this, we have take a look at the conduit bonding. That's crucial to safe installation. You can see this is a plastic enclosure. So it's metal conduit, so you have to make sure that the metal conduit is bonded on each side and is bonded to the ground lug in the enclosure. And so you'll also want to check for proper conductor sizing and markings, as well as fusing requirements. Fuses have to be rated specifically for solar PV. You can't just use any DC fuse. And one thing to keep in mind is fuses are supposed to be rated for 600 volts DC for residential or 1000 volts DC for commercial. And so lastly, for string inverters, we'll take a look at the labeling requirements per NEC 690. This inverter right here has a disconnect handle built right into the inverter. It also has to be labeled as a DC PV disconnect, and also that it has a rapid shutdown feature. So you can see that here it's PV DC disconnect and it has the rapid shutdown. Labeling is very important for future maintenance, and electricians working on the system, so they'll be aware of the specific hazards that the inverters or the enclosures have, and it also applies to first responders. So next we'll take a look at the AC combiner panel. This is where multiple arrays on a roof may be connected, and they get combined into a single feed before going into the interconnection. This is kind of similar to a sub panel, but it's a little bit different. So not only does the overcurrent protection need to be appropriately sized, which is these breakers here, the enclosure needs to be properly bonded and the neutral must be isolated from the enclosure. So in this case, the contractor did a good job of that. They isolated the neutral conductors from the grounding in the panel. You can see that all of the neutrals go to this neutral bar here, or lug, and then the grounding, the panel is grounded and the conduit is grounded as well. All right, so now the interconnections. Here we have kind of an example of a simple drawing of where a load side connection would be. Load side connection is typically a backfeed breaker or a sub panel. And this is where the inverter output is connected on the load side of the service. The service disconnecting means, like I said, is typically backfeed breakers, and they're typically located at the opposite side of the panel, the electrical panel, so as not to overload the bus bar. And so to determine an acceptable amount of current that can be placed in this backfeed breaker, you would use what's called the 120% rule. So you are able to have the main breaker plus the backfeed breaker, if you can add those up and it is less than 120% of the bus bar rating in the panel, then it's acceptable. So, and the whole point of this is so that you don't overload the bus bar. If you had the solar coming in at the top of the panel and the main breakers at the top, and you are using 120 amps on a 100 amp bus bar, there would be 120 amps moving through that bus bar, and that could overload it, and like I said earlier, cause melting or cause fire hazards. So for instance, if you have 100 amp service coming into the panel, and you have a 100 amp bus rating, you can have a 20 amp backfeed breaker and it'll still be acceptable. And if your bus bar in your panel is more than 100% of the main breaker plus the backfeed breaker, then you can locate the backfeed breaker anywhere in the panel. All right. So when we're looking at the load side connection, you need to look at your circuit ampacity right here, max output current. And this is located on the inverter nameplate that lets you know what the output current is for that inverter. You want to size the breaker and the wire to handle 125% of the rated output ampacity of the circuit. And this is crucial for sizing conductors and to ensure the bus used at the interconnect is not undersized. So you can see here the max output of this inverter is 16 amps. You would size it to 125% of that, so you get to 20 amps, and that would be a minimum of 12 gauge wire that can hold that amount of amperage. So the overcurrent protection, you want to make sure that the overcurrent protection device you use, whether it's a breaker or a fuse, is properly sized. That's vital to a safe code compliant system. And here you can see the standard calculations, just like in the previous one. To determine the sizing of the circuit breakers and fuses, you take 125% of the output current, and it's sized to protect the wiring and the equipment in the system. Most backfeed breakers like this one will be a double breaker. So they're 240 volt, which corresponds to what's in most homes. And you'll have equal distribution on each leg. All right, and once again, we see requirements for circuit identification. On the right side here, we see a good example of a directory right here, or right here, sorry, for a microinverter system that includes a color-coded map to tell which arrays go to which circuit. And then this specifically shows which modules are in which circuit, and that helps for easy maintenance and troubleshooting later on. And here you have a kind of a list directory, which is on every electrical panel in existence. And it's supposed to be filled out. Many times it's not, but you should make sure that it is, because that's important for future maintenance and making sure that everything is labeled and people working on it in the future know what they're looking for. And it's important that it should be legible. This is okay, but it could be a little bit nicer. All right, so here's a simple look at a load side connection calculation that's used to determine if the panel board is large enough to accommodate the PV system. Like I said, this is known as the 120% rule. So we have the inverter current. That's the output of the inverter is 14.4 amps. Sizing the breaker for 125% of that, you get to 18 amps. The main breaker is 100 amps. So you look at the main breaker plus the PV breaker, that comes to 118 amps, and the bus bar is 100, a 100 amp bus bar. So because it's not at over 120% of that bus bar rating, this is okay. And so that's like I said, it's important to make sure that the breaker is at the bottom of the panel, to make sure that the bus bar, at no point in the bus bar is it above the rating of that bus bar. All right, so the other type of disconnect or interconnection is a supply side connection. This is when the inverter output is connected on the utility side of the main service disconnect. This is also referred to as a line side connection or a line side tap. Since a supply side connection is very similar to a new service entrance, the NEC requires that the disconnect be rated for such, which would be here, and it must contain overcurrent protection, fuses, or circuit breakers, which you can see here. And at a minimum, the fault current rating should match that of the existing service equipment. And it needs 60 amp rating for entrance conductors per code. That's very important. That's a code requirement. So you have to make sure that the entrance conductors coming in over here are rated for 60 amps. All right. And this is one that we should be able to get fairly easily, since I literally just said it. A supply side connection must have a service rated disconnect switch with a minimum rating of 30, 60, or 100 amps, or none of the above. You can put that in the chat. I'm going to get it. We're a little bit over halfway through, but we should be able to move a little quicker soon here. So we'll keep going. The correct answer is 60 amps, which we just talked about. With the supply side connection as well, you have to ensure that the conductors are sized appropriately, that you do that by checking the labeling on the wires themselves. And you look at the inverter nameplate for the max continuous inverter output current right here. You multiply that by the 125% of the continuous load, and then you verify the labeling on the conductor to make sure that it can hold that amount of amperage. Another thing in the code is it states that the length of the supply side conductors can be no longer than 10 feet in length unless other means are taken to protect them such as current limiting devices. You can see here at age where the inverter output is fused and changed to service conductors, which are 60 amp rated, and they go over to the breaker panel through the conduit, and that length can be no longer than 10 feet. So in light of the fact that the supply side conductors are similar to a second set of service entrance conductors, and that they are unprotected from supplies or utility side current potentials, the disconnect that serves the supply side connection must be bonded similarly to a service panel. And in service panels, the neutral and the ground are bonded to the enclosure. So they're bonded together and to the enclosure. You can see here the ground wire is the bare wire, and the neutral wire and the ground wire are bonded to it via this bonding screw, this green bonding screw. And this allows the overcurrent protection devices to operate properly, and it also grounds the enclosure. Here's another example of a supply side connection. The main difference here is that there's no bare ground conductor. The green conductors are the ground conductors, and you can see it clamped together on the left side over here. And if you have ferrous conduit, which is metallic conduit, the code requires that the conduit going in and out of the panel be grounded, and this is because typically these enclosures use knockouts, which are basically pre-punched, and there's very little material left around that conduit. So if there was a fault, it may be too much for that small amount of material to hold, and it would melt, and then it could cause sparks and fire hazards. So by bonding them together, that removes this problem. So here's some of the labeling requirements for this type of connection. You have a traditional electrical shock hazard that is probably on every single electrical panel, and you have the PV AC disconnect also. The PV part of the code has some of the heaviest requirements for labeling that there is, and it's important to maintain the safety of the system, so definitely familiarize yourself with that part of the code. And also you want to make sure that there's a plaque or some kind of label showing that there are two potential sources of energy coming into this panel, so that if someone comes in, an electrician later on comes in and needs to use the shut down the panel, if they shut down the main disconnect but they don't shut down the PV disconnect, that panel is still potentially energized and it could cause shocks. All right, so which of these options is not an accurate description of a solar PV system? You can put your answer in the chat. And then give a few minutes here, or a few seconds, time for a few minutes. As you may have guessed, it's the answer that's not is a load side connection with a capacitor diverter, because we didn't talk about any of those, and that's not a solar PV system. So next we'll jump into the labeling requirements for solar systems. The New York Sun Solar Guidebook will that has a detailed labeling guide. It can be very challenging even for experienced contractors. Things to remember are the labels have to be durable and placed in manufacturer recommended areas and not covering other labels. And colors are predetermined by ANSI and OSHA, and you have to use the correct coloring. And another thing to keep in mind is the most dangerous label is a wrong label. Missing a label is bad, but it's even worse to have a wrong label, because that'll give the person working on the system a sense of security that they know what's there. And if it's wrong, it can, cause shock hazards and potentially injuries or death. So you need to make sure that you have all your labeling correct, and make sure that none of them are incorrect. So now we'll go through a bunch of examples of labels. One thing to keep in mind is all of the solar PV signage is yellow, orange, or red in color. And that's so it's easily identifiable for electricians and code officials to find. So here we have kind of your standard arc flash and shock hazard label. It's required on electrical equipment, switchboards, panel boards, control panels, meter enclosures, and motor control centers that are in other than dwelling occupancies. So arc flash hazards or warnings are very important because arc flash incidents can cause death, and if not, they can cause serious injury. Another thing that you have to label is the service disconnects. They have to be labeled with permanent plaques. You can see here, this is a great example because it has service disconnect 1 of 2. So whoever's working on it knows exactly how many there are, and it identifies which one it is. So you have the utility disconnect and the solar disconnect. And this ensures that anyone working on the system knows how to shut down the system later on when they're working on it. And also for a supply side connection, it requires a directory of the location of each service disconnecting means. You can do that through just a label like over here on the left, or you can have like a small map showing where each disconnect is. And this is, again, so someone working on the system later on can know exactly how to shut down the system and make it easy for people working on the system later on. All right, so next, the NEC requires these markings on PV system disconnects, depending on the disconnect you have. If it's AC, you would have this one. If it's DC, you would have this one. And traditionally, if you shut off the disconnect to a system, the power will be off. But if you shut down the main disconnect and not the solar disconnect, if the sun's out, it's entirely possible the system will still be energized. If you have a load side connection, so it's very important to make this clear. And so remember that the labels have to be suitable for the environment they're installed in, and the labels should be expected to last the life of the system. If you have this and it's a flimsy label, in 10 years it's gonna not, you won't even be able to read it. So it's basically worthless at that point. You need to have electrical shock hazards on all of your switches and circuit breaker panels as well, so people understand that there's a hazard and to be careful. This is pretty logical, makes perfect sense. And so next we have for inverters, anytime you have an inverter output, that's known as an interactive system point of interconnection. And you have to label with the rated AC output current and the nominal operating voltage. And one thing to keep in mind is NYSERDA does not allow writing on these labels. Engraving or printing on it is better, as the writing will fade and basically disappear by the end of the system life. 25 years from now, you would not be able to even see a written value. So you would need to engrave it or have it printed on the label. I think I mentioned this earlier, but when you have DC wires running through conduit, you have to label it every 10 feet to make sure that whoever is working or whoever's in the vicinity knows that they're there. Many people will not like the look of this, so they run the conduit down through their attic where no one can see it, or they use microinverters so they don't have to see that, because the microinverters will convert the current to AC current right at the panel, and then you don't have the DC conductor labeling requirements. Next, we have the direct current PV power source label, and that has to be on an inverter integrated DC disconnect or a DC combiner with a disconnect. It gives important system information to those who will maintain and repair the system in the future. You have to include the max voltage, the max current, and the max current of charge controllers if it's installed with energy storage. Here's an example of the required labeling at the interactive system point of interconnection. You need the AC output current and the AC operating voltage. A lot of times these are missing, incomplete, or not suitable for the environment. But many manufacturers make labels that will endure outdoor conditions such as wind, rain, snow, or UV degradation. So make sure that the labels that are installed are rated for the system, or for the location and the conditions, and make sure that they're accurate. Here we have the rapid shutdown requirements. The red is for string inverters, and the yellow is for DC optimizers and microinverters. New York City adopted the 2008 or 2011 National Electrical Code, which doesn't include rapid shutdown. I don't imagine anyone in the Adirondacks will be inspecting a New York City solar installation, but you never know, I guess. But NYSERDA has accepted the 2017 NEC. So since they're providing incentives for the systems, typically, they're able to specify that a rapid shutdown be installed, even though it's not included in the current minimum New York City code. A contractor could get around this requirement if they opted to not take the NYSERDA incentive, but it's typically pretty generous, so I doubt that would happen. And so that's rapid shutdown labeling requirements. At the point of interconnection, you need to excuse me, identify all sources of power being supplied to the bus bar or the conductor, and label it that shutting down one disconnect doesn't necessarily shut down the whole system. And this may be the first indication for someone working on the system that PV is installed on a building. This is another label required by NEC and OSHA. It's a pretty self-explanatory one. Just like the other ones, you need to make sure all the disconnects are closed before working in a panel to avoid it being energized while you're working on it. This is for a backfeed breaker. It's a power source output connection label. It specifies that these breakers should not be relocated because they typically, as I mentioned earlier, are on the opposite side of the panel as the main disconnect. And here we see the requirement for identification of circuits. This directory was not filled out, and that's necessary to assist future electricians in their maintenance and troubleshooting work. This is not part of the solar code, but just the general electrical code, which has to be obviously followed by solar as well. And so question number 7, which of these options does not describe a PV warning label? And we'll jump in. As I mentioned earlier, all the PV warning labels are red, orange, or yellow. None of them are green with a white background. So there's that. We're just going to go over quickly photo inspections. Can a comprehensive inspection be done by looking only at photographs? Yes, but the quality depends on the quality and the comprehensiveness of the photo collection. Photo inspections are through the quality assurance program, and they're used to save dollars by not making someone do an in-person 4-hour inspection. Something to keep in mind is sometimes well-built systems would fail a photo inspection because the quality or quantity of photos was too poor to make a determination. And so NYSERDA has been doing these types of photo-only inspections for a long time now. Permitting authorities can choose to require photos to supplement an in-person inspection to avoid making multiple trips to a site and to save time and money. Photos can kind of tell a story of how things were constructed and save the inspector time. It also improves inspector safety by reducing exposure to hazards like ladders and energized electrical equipment. The contractor may include photos of trenches and walls before being closed up to reduce the number of trips required to go to a site for a code inspector. So NYSERDA has implemented photo-only inspections with a lot of success. They can be a great cost-saving supplement to a process that's already underway. And if an inspector can review photos that tell the story of an installation, this can save the inspector time by not having to climb on the roof or open every single enclosure. Like I said, inspectors can complete the inspection in less time and spend more time in areas that they've identified as potentially problematic. Like I said, if there's trenches or walls that are going to be closed up by the end of the installation, the inspector can look at the pictures and not have to go multiple times to a site. So what are some reasons to use the photos to supplement inspections? We have about 30 slides left in about 30 minutes, so we'll just keep moving through. I'm assuming since we just went through this, people are getting this, but the answer is all of the above for the reasons I just went through. All right, so now we'll go through some of the most common installation errors that we've seen over the 4,000 inspections that have been done by NYSERDA. So we talked about this several times already, but it's important to ensure the system grounding is done properly. It could be the clamps are loose, or the integrated bonding system is not compatible with the panel racking system, or they're just not using the bonding system correctly. But if the system is not grounded, it can cause serious injury or death. So it's very important to get right. Now they have some solar panels that have plastic frames and they don't need to be grounded. But you still have to make sure that there's a good bond path through the system. At the array, the bonding and grounding are very important. It provides the pathway for fault current to open an overcurrent protection device or to be detected by the fault detection equipment, which will disconnect the fault from the system. So here we see an integrated mid clamp that provides bonding of all the modules, except for in this installation, there was one single module placed by itself, which would need a separate bonding method, and that they did that using end clamps. And there are other methods, such as weave washers or star washers, that may also accomplish the bonding and grounding, as well as actual lay-in lugs, which we'll see a little bit more in a minute. So here's an example where a contractor attempted to accomplish bonding requirements with copper lay-in lugs on aluminum frames. And you can see that they've corroded and actually broken away from the module. So also notice the reaction between the module or between the copper conductor and the aluminum frame in the upper left here. Do you think that these two modules are effectively bonded together? I think it's pretty obvious that the answer is no. And something to keep in mind is this happened just between the time between the build and the interconnection and the QA inspection. So the screw had already corroded to a point where it broke away from the panel frame in that short amount of time. So if the equipment's not rated for use in the environment that it's installed, it can fail very, very quickly. Here's a situation where the bonding to the rails was accomplished through a self-tapping screw, and this would actually fail. And the reason for that is because the lug or the screw used is not rated for bonding purposes. I mean, you typically need a fine threaded machine screw that has a minimum of two threads in contact with the metal. So this had too coarse of a thread, and so this would fail code for that reason. One of the most common installation errors on a rooftop is where the conductors are not properly supported and are just laying on the roof, and they're subject to damage by wind, snow, ice, movement from wind, and especially they rub against the abrasive shingles they're in contact with, and that can cause the wires to fail. Another potential hazard in this kind of situation is squirrels or animals nesting underneath the panels. They like to chew on the wires. And what you can do about that is install critter guards, which are basically metal or plastic mesh that surrounds the array and blocks the critters from getting between the array and the roof. And another thing to keep in mind is the wires can also catch debris, which can cause drainage issues and then cause problems with the roof. So you want to make sure that all the wiring is supported and inaccessible to animals. Again, we talked about having the correct equipment for the application. All conductors and fuses should be DC rated and should be rated for PV. Like I said, residential, you want 600 volts DC rating, and commercial would be 1,000 volts. Here's another common error where fittings used for conductors to enter an enclosure are missing or not installed. You can see over here the fitting is not tight to the wire, so it doesn't provide the stability that is the point of that kind of connector, and so that would fail for that reason. On the left, some of these wire nuts are not rated for outdoor conditions, even though this is kind of inside the enclosure. They're not. It's an outdoor. It's the humidity and the temperature is the same as outdoors, so it's essentially an outdoor space. And also, you're supposed to run the wires through the knockouts in these systems, and they ran the conductors right up underneath the lid, which is obviously not okay. So this would fail for that reason. Here you can see examples of galvanic corrosion. Many contractors underestimate the effects of galvanic corrosion, and that happens with the direct contact of dissimilar metals. Here are two situations where copper conductors are in contact with a dissimilar metal in a wet location, and it's clear that the conductors are quickly corroding and deteriorating. You can see it more over here, but up here you can see just the beginnings of it. And a way to avoid this is to use insulated conductors, or there's other methods as well. Here we have the raceway is being used to support a conductor, which is the ground wire. And code is limited on what conductors you can have supported on the outside of a raceway. You can also see the galvanic reaction between the copper conductor and the coating of the raceway. The ground wire will eventually corrode and eventually deteriorate over time, and that'll cause a failure in the grounding system. Basically, the only thing that's allowed to be attached to the outside of conduit is like data wires, which are typically low voltage. Here we have examples of conductors that are not being protected from physical damage. You can see the sharp edge of the panels and the racking system, and also the roof, the shingles. These will, the shingles are abrasive to the wires, and this should have been run through conduit to get around this edge. As it is now, they will rub on the shingles and will eventually, wear away and cause the conductors to fail. Outdoor enclosures, they may need what's called a weep hole installed. And this is an effective way to allow water to exit an enclosure to avoid pooling. Weep holes are used to prevent moisture from accumulating in the enclosure. So you can see here the water line kind of ends right where that weep hole is, showing that it did effectively drain the system. These obviously should not be sealed, as they're specifically to let water leave the box. So if you see a hole like that in an enclosure, it's not a violation. It's part of how they allow drainage to happen. So here's an interesting situation. Here we have an outdoor rated enclosure that was simply not properly installed. Can't really see that in this picture, but the conduit entry point isn't properly sealed at the top of this enclosure. So that allowed water to get into this, and you obviously don't want water in your electrical system. But since they did this inspection in the winter, the water had frozen, and you can see that it pooled in the enclosure, and it just built up until it was able to go down one of these conduits, which obviously you do not want to have in your system. You don't want water in your electrical system at all. And so here we have an enclosure that's not only suffering from water buildup, but the lugs on the conduit are not rated for the wet environment. You can see that they're rusting, and the wire knot terminations are also not rated for the environment. This is a location that would be well served by the installation of a weep hole to drain any excess water accumulation. And on the right, you can see that the conduit is not oriented in a way to prevent water entry. So this is a flat roof, and the conduit is kind of angled up, which is basically, it allows for when it rains, the water will just go right in and drain down into that enclosure, which is obviously not a good thing, as I mentioned like several times already. So yeah, I mean, this would definitely fail based on that. Here we have an example of conduit passing from the outside to the inside of a building, and it's not sealed. There's a potential for condensation buildup where the warm building air meets the cooler outside air, or vice versa. And once the condensation forms, it has no place to go but down the conduit into the panel that this enters into. And there could be live circuits, and water and electricity is not a good combination. So you want to avoid that. This is a violation of the electrical code and the energy code, since there's an energy component to it. We saw an example of this earlier. This is metal conduit going between two non-metallic enclosures. In this case, you would need to see the conduits each bonded and grounded to maintain grounding throughout the system. And you do this through a grounding wedge installed in that panel. Here we see a non-contact voltage tester used to determine if the disconnect is wired backwards. It is. So you'll notice that the disconnect is open here. These are up, and yet the bottom of the disconnect and the fuse are still energized. This means that this disconnect was installed with the conductors going in the opposite way that they should be. These ones on the bottom should have been installed in the top because they're always energized. They would be from the utility, and then the bottom would be from the solar system, basically. And that allows for the fuse to not be energized when the thing is open, when the disconnect is open, so that the fuse can be changed. And one thing to keep in mind is the non-contact voltage testers don't always work on DC voltage, so you need to be careful that you are not solely relying on that. Here we see a supply side disconnect means that does have a proper neutral to ground bond. You can see the white conductor and the green conductor are bonded through this green bonding screw. And that's done correctly for the AC supply side connection, as you can see right here. Another potential problem that we see is terminal ratings need to be followed. Terminal lugs where you land wires are rated for conductor size and max number of conductors. So here we see a main breaker where conductors have been doubled up on terminals rated for a single conductor. In this case, we need to check the ratings on the terminals to ensure they're rated for 2 conductors. You can see that here and here. And on the left is the circuit breaker. This is the main breaker conductors, and this is the circuit breaker conductors that have too many connections installed in them. These labels are required when the 120% rule is in effect, and it's used to add PV to the bus in excess of its rating. And like I said, this requires that the additional power being supplied to the bus is located at the opposite end of the bus so as not to overload the bus, as we've seen already. Feeder taps are a type of interconnection that requires special consideration, sort of a hybrid load side connection. They have the potential to add additional available current to conductors and bus bars, and we need to consider this. In this case, in order to protect the conductors from the additional PV current, an additional overcurrent protection device has to be installed. This is covered in Article 705 in the code. And here we have an example of this. We see the interconnection on the load side of the 200 amp breaker on an apartment where the apartment panel didn't have a main breaker. And you have a meter pan, which is basically this, with an integral disconnect. The existing conductors and possibly the bus bar downstream can be strained by this additional current. So potential solutions include conductors and bus bar increased in size for the new additional current, or additional protection by adding an overcurrent device before the loads, such as a main breaker in the panel. You would have the PV voltage tapped into the utility line coming in, and those taps connected to a disconnect. Then you would have a main breaker on your electrical panel so you don't overload your panel. And these are not very common, but there are places where you do see it. The left-hand picture is an improperly sealed roof penetration. The contractor drilled through the roof, and then rather than sealing it properly, used duct seals, which is not an appropriate way to seal the opening. It doesn't look great, and it's basically putty that goes around the hole. And it's somewhat weatherproof, but it's not being used correctly here. And on the right, we see the correct piece of equipment that should be used for this penetration. There are two applicable codes, the New York State Residential Code and the New York State Building Code. And depending on the occupancy, if it's residential or non-residential, specific information on flashings can be found in the roofing section of the checklist. Here we see an interesting situation. Here, these are two pictures of the same panel. You can see the left lug looks normal, but the right lug is discolored, and obviously the insulation is in terrible shape. What happened here is the right lug was not tightened down correctly, and the wire was loose in the lug, so it didn't have a good connection. And the temperature of the wire went back and forth, and it burned off the insulation. Then since it's outside, condensate got in there and caused the copper to corrode and flake off. The only way to fix this was a complete replacement. So we don't know if the copper shards fell down into the breakers, causing them to fail. So the only way to fix it was the contractor had to come and replace it all. So that lug should have been torqued down to the value specified by the manufacturer. And so here we have an example of this is one of a few homes in Boston that had natural gas explosions, and you can see that the roof is more or less intact, and that's because some people theorize that the racking system on the roof may actually make the roof stronger. And this is just kind of for interest. Because it's ironic that the only thing that did survive this house was the PV and the racking systems. And keep in mind, structural issues should be addressed by a New York State licensed professional engineer or a registered architect. And so here we have a couple new products. This is what's called a Connect DER, which can eliminate costly interconnections and reduce installation errors for supply side connections. This was experimented with in the Con Ed territory. It's installed by the utility, and it's the point of interconnection, and it gives real-time solar generation data for forecasting. This requires that the GEC connection be made in the meter pan, and the 2020 NEC requires that all meter pans have a non-fused disconnect switch so that the meter can be serviced. So that may change where the point of interconnection is. And this also allows contractors to install PV to stay outside the home while installing the system, and they don't even have to go in your home. Here we have micro flashings, which could be a potentially good piece of equipment that would allow cheaper system installations to seal penetrations of roofs. Normally, you would not want an electrician doing the flashing on your roof, but if these work and they're installed correctly, then this could help reduce the amount of resources needed to do the installation. There's a lot of additional resources available. Obviously, there's the solar guidebook that we talked about today. There's also the QA checklists and guides that are available through NYSERDA's website. And lastly, the energy storage guidebook, also available through NYSERDA. And they're all available publicly, and you are welcome to take advantage of those. And lastly, here we have, this is at Hudson High School. They have a solar array on their property. It's a 1.2 megawatt system. And you can see it's a little bit bigger than the athletic field. So it's a good visual for how big these systems are. A 1 megawatt system is about as big as a football field with the track around it. So are there any questions?
If there are any questions, please go ahead and write them in the chat. I don't know if we saw any, Chris, early on. I was keeping tabs, but there were so many other answers to your questions.
Yeah.
That I'm not sure I got any. So if we didn't see it, please enter it again in the chat, folks. And we're a small enough group that if you would prefer to unmute and ask with your voice, that's fine too. There is one question, Chris, do you see that one?
How much
Can you-
applies to non-interconnected systems? Well, I would say basically everything apart from the interconnection, right? So you still need to make sure that all of the wiring and the system components are compatible and they're the size correctly for the system. So basically everything except for the interconnection would still be applicable.
Any other questions? Chris, you gave out a lot of information. There's a lot to digest.
And it like I said, if anyone does come up with a question that they find or you think of after this, you can email me. So my email is cdoty@frontierenergy.com. And if Nancy, if you want to include that in when you send out the slides, then people have it
Sure.
available.
Yeah, I can do that. And everyone will have the slides. As a reminder, I'll be sending out another email with the slides, so you can find Chris's email address always there, as well as I'll add it to the email itself and a recording of tonight's webinar. It doesn't look like there's more questions unless I missed one.
Okay.
So, but I will just mention, there's just one popped in there. Can you read that from Carl?
It appears that only contractor installed systems can qualify for NYSERDA benefits. I believe that is correct. You could use this information for homeowner installed systems, but you would not likely qualify for a NYSERDA incentive.
Right, that's the New York Sun incentives that NYSERDA gives, a per watt incentive.
Right.
But that's an issue that the homeowner contractor works with, and not the town or code enforcement, as far as I understand.
Yeah.
I will just mention about the New York State Unified Solar Permit that Chris mentioned, I think at the top of the webinar. This not only is adopting this streamlined permit easier for your code enforcement team, it also qualifies as a Clean Energy Communities action item. And I didn't mention it much at the beginning, but the Clean Energy Communities program is, encourages municipalities to take actions, including things as simple as adopting the Unified Solar Permit, and it helps to build points so that your community can earn no cost share grants. So very easy action to take, and I can provide you with that permit as well as a sample resolution to adopt it. Many communities are adopting the permit because it streamlines your code enforcement and asks all the right questions. So please get in touch with me if you're interested in doing that in your community. And then I'll mention that the next training in the series is the week after next. We're taking the Thanksgiving holiday week off. And it's called Overview of the Model Battery Energy Storage System Law. And it's on Tuesday, November 29th. And then the last one in the series is Battery Energy Storage for First Responders on Monday, December 5th. So if you'd like to learn more about battery energy systems, storage systems, then please tune in for either of those sessions. And just as a reminder for those code enforcement officials looking for Department of State credit, the session on the 5th also offers 2 hours of in-service credits. So, and I'll remind everyone again, just so there's not too much confusion, that if you haven't signed up for the next sessions, please do so. The registration's still open, and that there will be a different Zoom link for each session. So if you got onto this session, then you've gotten past that, but just to keep things from getting too confusing. Otherwise, again, thanks you for coming, and thank you, Chris, very much for giving all that information. Lots to digest, and happy Thanksgiving to everybody.
Thank you. You too. And thank you for having me.
You're welcome. Good night, everybody.